And our next talk will be on ontology knowledge enhanced in context learning for action effect prediction.
And hi, everyone. I'm Fangjun. So can everyone hear me?
Yes.
Thank you. I'll share my screen with you. Okay, so I guess you can see the screen now. Sorry. Hi, everyone. I'm Fangjun, and it's a pleasure to present our recent work, the ontology knowledge enhanced in context learning for action effect prediction, which I work together with my two supervisors, David Hogg and Anthony Cohn. And our action effect prediction task, it takes linguistic description of the preconditions and actions as input and generate another text that describing the post condition. So that's subsequent world state following the action. And one example here, given the action description, a cook is cracking an egg against a glass ball. We hope a model would be able to generate after cracking egg, the inner content of the egg will be in the ball and so on. So that's a subsequent world state. And for these action effect prediction tasks, researchers have been working on this problem for over a century. First, based on the physical reasoning. There is Ernie Davis egg cracking problem. The researchers go into great detail about the possible results of an action in various situations. And following that, researchers research on actions in robot systems. We try to depict actions and their effect on objects in symbolic representations that can be used in robot systems. And with the rapid development of language models, there have been some studies on reasoning about actions with language models. And for the action effect prediction tasks, they created specific datasets and they trained transformer-based language models. And in recent years, there have been studies that combine physical model with language models to reason about actions. And the data from various studies varies in quantity and level of detail. And actions description, they can range from verb noun phrase to sentence to a paragraph. And in this paper, we look at the following two datasets. First is this 1,400 action effect pairs dataset with effect descriptions for 140 actions. So there are 10 effect annotations for each action. And the description of the action is a verb noun phrase. And the prediction, that's a sentence. Second, there is a Piglet dataset, which had 2,000 interactions, 500 for training, 500 for validation, and 1,000 for testing. We see here one example, both condition and action description, they're provided in sentences. And the prediction is also a sentence. The primary problem is figuring out how to use diverse small-scale datasets. Our method is based on large-scale pre-trained language models. That's a PLM. That's large neural networks that have been used in a variety of natural language processing tasks. They operate under the pre-trained fine-tune paradigm. The model are first pre-trained over large text corpus, for example, Wikidata, which supplies the model with basic understanding capabilities that can be easily used for many downstream tasks by fine-tuning downstream dataset. And from Elmo, BERT, GPT, Mac-trained Turing, and NLG, these models grew in scale and power over time. And this paper will focus on GPT-3, this 175 billion parameter model. That's the third iteration of the generative pre-trained transformers family. But our method can be applied to other pre-trained language models. And the latest development showed that the data limitation problem can be overcome by the few-shot learning that's providing a few examples at inference time with a large language model. So what is in-context learning? In-context learning was popularized in original GPT-3's paper as a way to use language models to learn tasks given only a few examples. During context learning, we give the language model a prompt that consists of a list of input-output pairs that demonstrate a task. At the end of the prompt, we will append a test input and allow the language model to make a prediction. And they are short, one shot, few shot. That's depending on how many example demonstrations are provided at the inference time. Here we see GPT-3's test set performance on the superglue benchmark, that is a common sense reasoning benchmark. With the in-context few-shot learning, given 32 training examples provided for all tasks, GPT-3 outperforms a fine-tuned BERT large and BERT++. And though there is still a long way to go before reaching human level and fine-tuned state-of-the-art, we're curious about how to improve GPT-3 few-shot learning ability on our task and the approach we worked on that is called prompt engineering. First, let's discuss some terminologies. A prompt that is a paste of text inserted in the input examples so that the original task can be formulated as a language modeling problem. And the later part, prompt can be a description of the task. And a template, that's a function that maps an input to a text. The prompt engineering, that is a process of creating the template that results in the most effective performance on the downstream task. There are many different possible templates for the same task. In practice, it is better to use templates that make the sequence closer to the language modeling, that is closer to the text that a model might have think during pre-training. And we design different templates for these two datasets. And for this 1,400 action effect pairs dataset, we add the person before action phrase and add as a result before the effect prediction. For example, here, this one-shot learning example, the person baked potato. As a result, potato is heated in the oven, so it can be eaten. And the test inference test is the person kicked door. As a result, the model will generate the consequent tokens. And for the piglet, we keep the format of precondition descriptions and actions that's depicted in X here, and add therefore before that effect description, and also one example. We're interested in finding out how we can improve GPT-3 few-shot learning ability on our action effect prediction task. And existing research suggests that incorporating common sense knowledge into language model may lead to more successful few-shot learner. And according to the early model, as of 2019, pre-trained language models neglect to incorporate knowledge for language understanding. And according to research evaluation results in 2020, there is a large gap between the pre-trained language models and the human level common sense reasoning. And the common sense knowledge embedded in pre-trained language models is still insufficient for common sense question answering in 2021. And the direct fine-tuning of pre-trained language model yields suboptimal results according to 2022. External knowledge graphs have been considered as an indispensable part of language understanding. We develop our knowledge enhanced in-context learning method in this work. In the original in-context learning without external knowledge, the action prompt is sent to GPT-3 and the output text is used to predict the fact. In our knowledge enhanced in-context learning, the textual knowledge pieces together with action descriptions are employed as input to the GPT-3 model to do post-condition prediction through in-context learning. And specifically for this action effect task, we employ NeuRob ontology as our knowledge source. This knowledge base is supplemented OpenSec with additional knowledge about human everyday activities and household objects, and thus matches our requirements for use in action effect inference task. And this ontology knowledge, they have one problem. They're intended for robot systems. So how to apply such symbolic knowledge is a critical component of our work. And we see this pipeline, we developed this knowledge processing pipeline to solve the two key problems. First, the NeuRob ontology knowledge is intended for robot system. How we apply such symbolic knowledge into language model is a critical component for work. And what we did here is first retrieve knowledge, and then transform knowledge to text. The second problem is NeuRob, that's a fixed knowledge base. Thus, it has the knowledge incompleteness problem. That means there is no explanations for some terms, how to obtain knowledge for concepts that don't have definitions in this fixed knowledge base. That's the second challenge. To solve this problem, we conduct the unseen knowledge learning with GPT-3. And I'll dive into these three components in the following part. The first step here, the ontology knowledge retrieval. That's retrieving action object relevant ontology knowledge from NoRob. And when we introduced before that, we used two data set. That's 1,400 action effect pairs data set. From that data set, we got 62 verbs. That's action verbs, and 42 nouns, that's objects to be manipulated in total. And for Piglet, we got an n-gram list that for each sentence we will extract words. And we retrieve the ontology knowledge for these 62 verbs and 42 nouns from NoRob. The knowledge are stored in the web ontology language, that's OWL triplets. So that's the subject, relation, objects, and the most common predicates in the NoRob, that's a subclass of, and we use verb and noun from action phrases as subject, queried with SWI prolog using the subclass of predicates, and it returns the objects that matches for our specifications. And for the 62 verbs and 42 nouns in this dataset, there are 10 verbs and 9 nouns contained in the NoRob ontology. And here we show detailed retrieval result for the verb mixing. It got incorporation physical, you see here, and the description 8A3 and the description 8A4, that the objects it returns to us. And with retrieved information, we could find the original knowledge pieces in the NoRob ontology file. But these are in extensive markup language-based format, that's XML format. And then comes our second step of work. We will try transforming these XML-based format knowledge pieces into plain text. We map all retrieved ontology fragments to attempt to control the English text to use the OWL syntax converter tools and the OWL verbalizer tool. And then we transform the ACE text to plain text. We insert a space before each uppercase letter and convert all the letters to lowercase, removed the subclass description area and replace the abbreviation STH with something and concatenate all the text to form a single sentence using a comma. And after the previous two steps, we obtained the ontology knowledge statements, the 10 verbs and 9 nouns from NoRob. But we know that the two datasets, they contain more atoms that don't have explanations in NoRob. So how to get the knowledge for those times? What do we do here? We address this challenge by utilizing GPT-3 to learn previously unknown ontological knowledge. Our retrieved knowledge for verbs and nouns form the A part, that's answer part, in each question answering pair. And there are 19 example input-output pairs in total. And given the task description, the verb noun example and their knowledge definitions, finally with the query prompt, GPT-3 will generate its version of knowledge for a new word. And we use this context learning method to generate knowledge descriptions for the remaining 52 verb and 33 nouns in this 1,400 action effect pairs dataset, and generate knowledge for all words n-gram list in the Piglet dataset. So after this step, we got the full ontology knowledge base for the two dataset. The final work is embedding this knowledge into the prompt. Since the generation of each word is in the sequence is based on the word itself and all preceding words, what we do here is we prompt the model with the knowledge statements by prepending the knowledge pieces before the action-related description. Here we present one complete instance for each dataset. The colored boxes represent obtained ontology knowledge. Brick means, window means. For Piglet dataset, we begin by extracting a concept list of action description sentence using matching 1 gram. For example, here for this sentence, the robot turns the stove knob to the on positions. We will get the list robot, turn, stove, knob, and position, and we will prepend the textual knowledge statements before the precondition sentence. So that's all about our methods part. And in our experiments, full knowledge source settings are compared. The first is the pure language model without external knowledge, and then COMET, that's common sense transformers. We got the knowledge clarifications from this COMET knowledge graph, and the concept net, that's knowledge clarification we get from concept net knowledge graph. And we extract relation paths between words from the precondition description and words from the action description. And it's the NOROB, that's our approach. And the evaluation, we use BLUE and the BERT score as evaluation metrics. BLUE measures the overlap between the generated response and the ground truth, and the BERT score, it evaluates the text generation by computing token similarity with the BERT model. And we conducted few shot learning, that's 1 shot, 2 shot, 4 shot, and 8 shot. In this table, we show the result of Curie. That's the second largest GPT-3 model result. And better results are shown in darker color. Best results for each shot in bold. There is a trend of improving result when the in-context learning sample increases for 1 shot, 2 shot, and 4 shots. The prediction performance improves when exploiting completed ontology knowledge from NOROB. But especially for the full shot learning, there is a gain of over 4 BLUE score for GPT-3. But when the training example, increased to 8 shot learning, there is a slightly drop with NOROB for this dataset. We will explain why in the following part. We report 3 randomly selected full shot learning results from the Curie model for this dataset, which help us analyze what impact the imported NOROB knowledge has on the post-condition prediction. And for the 1,400 action effect period dataset, we see here the label represents the human annotations. The human annotations are always concise. And well, for some cases, it put more focus on the action process rather than the post-condition description. For example, here, Bentley, it says further lag in a way. It tells about the action rather than the post-condition. And we can see that with Curie, both generations without knowledge and with NOROB enhanced knowledge are acceptable, but the generations without knowledge prompt tend to contain some not everyday terms. For example, here for Cohn, it produced text such as enzymes are denatured. And one problem we observed from the table is there is a drop with knowledge enhanced 8-shot learning. So why that happens, we give them example here. With more training examples, the pure language model generations become extreme simple, quite close to training example format and label format. The knowledge enhanced input output compared with the baseline generation is more complex that may contain further information. For example, here, big potato until it's soft. Bent knee, bent at the joint, and cook onion then being left to sit in the hot water. These tokens bring lower token similarity score. And here, this table will show the results on Piglet, another dataset. And there is an improvement of the BLUE score and the BERT score for all cases, but the increment that is not so obvious. Here we show some examples of full shot learning of the largest GPT-3 model, the Da Vinci on Piglet. And here we show some examples of full shot learning. The human annotations are usually short, but contain the most important effect information. The no knowledge generation are short and relevant, usually explain the state changes of single object, but tend to be impacted by things that occur in precondition descriptions, but have nothing to do with the action. For example, we see this example here in the second. There is a plate in an open cabinet and the robot is holding a cup. The robot closes the cabinet. Apart from the cabinet, we see in the precondition description, they also mentioned holding a cup and a plate in cabinet. The prediction generated without knowledge plate inside the cabinet actually isn't the effect of closed cabinet, but put the plate in cabinet. And the generated post-condition exploiting NoRob contain more information, sometimes also affected by unimportant things, but they include the essential post-condition description. For example, the second example, the prediction is cabinet is now closed apart from plate is inside the closed cabinet. And we also compared the 8-shot learning result on 2 knowledge settings facing no external knowledge and with knowledge, with NoRob knowledge. The way we run our experiments on both sizes of GPT-2 models, small, medium, large, and XL with different parameters, and GPT-3 models, Babbage, Curie, and Da Vinci. We also show GPT-2's result here because we know that GPT-3, that's not public available. Access can only be obtained through an API, with users required to pay for token usage. But unlike GPT-3, the GPT-2 model can be accessed using the Hugging Face open source transformers library. And on the whole, there is an increasing trend in the BLU performance scores when the model size for GPT-2 or GPT-3 goes for the 1,400 action effect pairs dataset. GPT-2 large has the largest BLUs, blue score. And Curie model, that's the second largest GPT-3 model, got the highest blue score among all GPT-3 models. And the GPT-2 large outperforms Curie for this dataset. The best result for Piglet are obtained on the second largest site, the GPT-2, but largest Da Vinci, the GPT-3. But the blue score decreases when the model size is changed from GPT-2 large to GPT-2 XL. So one problem here, why Curie generate a better result than Da Vinci? Because we know that Da Vinci is the most powerful one. We are expecting it to perform best. The fact is that the Da Vinci is best suited for applications that require creative content generation and extensive understanding of the content. Curie excels in answering questions and generate chatbot, generate service chatter. And here we give some examples of the generations from Curie and Da Vinci. Da Vinci's generations are more sophisticated and is likely to produce usable output that is more complex, that explores higher level domain thinking and analysis. However, Curie, the generation here is computationalized, demanding, and more adequate and simpler. So Curie is a winner for these 2 tasks. And apart from the knowledge-enhanced few-shot learning, we also conducted fine-tuning experiments. We compared the NoRob knowledge-enhanced and few-shot learning result with the fine-tuning results of GPT-3 on Da Vinci model with the, we compare with the baseline, that's the PigPen analogy baseline. And the ontology knowledge-enhanced in-context learning with only 8 examples from the training set as input can achieve similar level. That's only 1.3 blues pound lower and 0.1 Bear score at 1 pound lower, which are trained on lower than this one, but they are trained on 500 training examples. And furthermore, fine-tuning the GPT-3 model on all 500 training examples with ontology knowledge produce a new state-of-the-art result. There is an increasement of 4.7 Bear score and 4.6 Bear score on the Piglet test set, even higher than the human predictions. But one thing we have to say is these 2 metrics, the blue and the Bear score, they're efficient methods of benchmarking, but clearly have shortcomings because the scores, they are based only on a set of reference sentences. And a high score that just suggests that the generation prediction coincide closely with the evaluation set of sentences, but the converse, it doesn't necessarily mean the prediction wouldn't be in agreement with other human annotations. Some generated statements which are in fact appropriate description may receive low score. And to sum up, we have worked on the action effect prediction task. We employ the pre-trained transformer model, the GPT-3, to solve this task. At the same time, we improve this language model's reasoning ability by injecting external knowledge from the strongly relevant ontology knowledge base and NoRob. and we converting the ontology knowledge into text prompt and demonstrate a new use for the traditional knowledge base. Such a generation task can have other applications, for example, on robot manipulation and combining with the visual information for further reasoning. And there are some interesting potential future work directions. First, in future work, we could translate the language predictions back to a formal ontology. This would allow automated ontology enhancement by exploiting the knowledge from language models. And furthermore, developing explainable pre-trained language models for allowing them to be deployed in cognitive systems. And third, try different settings of training examples and prompts, and finally extend to more complicated tasks, for example, quantity change predictions, data tracking, and action planning. And our code and slides can be found on this GitHub page. That's all for my presentation. Thank you.
So let me go ahead and start with a Slack question. Chris asks, when you say 2-shot, 4-shot, etc., are you referring to the number of examples in the training set, or are you looking at the number of examples in the prompts?
I got that. We have this page. When we say 1-shot, 2-shot, or 4-shot, we're saying, because we're sending a prompt to a language model. Let's see here, this page. When we give something that's a prompt to the language model, like to make the inference. And the example, if, for example, here is a 3-shot, we will form this text format and send this to the language model. So that it's at the inference time. There will be trainings, there will be training data and there will be text data, but the how many shots here means how many examples you give it at the inference time.
Okay, thank you. Go ahead, Pat.
Right, a comment and a question. So the comment is, I encourage you to never ever use the phrase few-shot learning. It doesn't make any sense. It's perfectly reasonable to report learning curves. That is, to show how performance improves as a function of the size of the training set. We've been doing that in machine learning since the 1980s. The new notion of a few-shot learning is just ill-formed and confuses people. And just report learning curves and don't put them in tables. Do plots. It's much more insightful. The question is, I'm trying to understand what your work tells us about the nature of the mind, about the key questions of cognitive systems. So you took a language model that we know is broken, does not work the way people do, doesn't get at reasoning in the sense that we're interested in it, and you try to fix it by adding some knowledge. What conclusions can we draw from this, as opposed to, I mean, why would you not build a common sense reasoning system and hook it up to some natural language system that we believe is closer to what people do? Why did you? What lessons should I come away with? Theoretical insights into the nature of common sense.
I got your question. That's a quite interesting problem. You mentioned that previously when we do physical reasoning, it seems quite a different way from what language models do, because language model, they're probability based and they
No, it has nothing to do with probabilities. It has to do with the fact that they're storing everything rather than storing pieces and then chaining them together. Mm-hmm. If they're caching all the results, you could do that with you could take a theorem proving system and you could create a bunch of lemmas, and then it wouldn't have to do reasoning in order to draw conclusions. It wouldn't be very interesting.
Yeah, we see that in recent years there have been a lot of progress in language models, and we see the capability of these language models. And what I'm trying to do is we're trying to bring what we previously have done in the past centuries. People have formed a lot of axioms or a lot of ontology, those things, but they seem quite different things from what language model does.
They are very different, and I ask again, what theoretical insights into common sense reasoning do you get from this work?
Sorry, I would just think that I'm trying to bring the conventional things into the language models. So that's a problem to be discussed, there are many ways you can make use of those common sense knowledge. You can have a try of that. And what we do here is that we use this by prompt engineering, that one way the language model can accept that the language model can use it as input.
I understood that you had a technique for improving the results from language models. I'll ask again, what theoretical insights into common sense reasoning come out of this work?
So I think we should actually move on to the next question, just to keep it going.
Please think about that, and we can talk on email.
Okay, we can communicate with each other on email.
So we have a question from Lucien who says, would it be difficult to convert the results to logical forms and evaluate those to get around limitations of measures such as blue? Predictions of a conjunction P and Q would not be penalized versus P unless Q is inconsistent with P.
So that problem is about the evaluation of the result, right? So here,
yeah, that's my understanding.
Sorry.
Sorry, yeah, that my understanding it is about the evaluation of the results. And could you get around the problems with blue by converting results to logical forms?
By converting blue to logical forms, you can understand blue. That's evaluate the text generation by computing token similarity. For example, for one action cracking egg with the action effect of cracking egg, it generates a piece of text, and there will be tokens, T1, T2, Tm, and there will be human evaluation, a human annotation, another S1, S2, Sn. They will calculate the overlap of the between the tokens.
So I think the question was actually about using a different method besides blue, but maybe in the interest of time, I will ask maybe perhaps you and Lucien can follow up on Slack, and maybe we'll go ahead and start the next talk. So let's.
Yeah. And the reason here why we use blue and bird score, because we want to make a comparison with the PigPen analogy, this paper. So that's why we can still use other metrics, and I do think metrics that's a valuable research direction, because I don't think these two metrics are enough. I also mentioned that they have some problems for some generated sentences that make sense, but they are not quite similar to the annotation sentences. They got quite low score. That's not sensible. So that can be another direction of choosing or developing other sensible and robust metrics.
Okay, thank you very much. Let's thank our speaker again.
Thank you.